All right, today we are pulling back the curtain on a piece of invisible magic. It's something that powers pretty much every piece of modern tech you use, and it's called digital signal processing, or DSP for short.
So let's just jump right in with a question, kind of like a riddle. What could possibly connect the sound of your voice, a digital photo on your phone, and the massive vibrations from an earthquake? I know, it sounds random, right? But believe it or not, they all share one incredible technology. And by the end of this, you're going to know exactly what it is.
Okay, first things first, we have to get our heads around a really basic problem. See, the world around us is just this constant flood of information. But our computers and phones, they don't experience it the way we do. And it all starts with this idea of a signal.
So what even is a signal? Well, put simply, it's just anything that carries information. Your voice traveling through the air? That's a signal. The electricity humming in a wire? That's a signal too. Even the light bouncing off something so you can see it? Yep, also a signal. They're all just physical things that change over time and carry some kind of meaning.
Now this is the really important part. The signals out here in the real world, like that smooth, flowing wave you see, are continuous. We call that analog. But our devices, they speak a totally different language. They talk in precise, separate numbers, kind of like those blocks on the right. That language is called digital, and the whole point of DSP is to be the perfect translator between these two very different worlds.
So how in the world does that translation actually happen? How do you take a smooth, continuous wave and turn it into a list of numbers that a machine can actually read? Well, let's follow a signal and see what its journey looks like.
This diagram here shows the entire trip. So over on the left, you've got an analog signal. Let's say it's your voice going into a mic. First, it hits an analog to digital converter, the AD box. That's where it gets chopped up into numbers. Then those numbers get zapped into the digital signal processor in the middle. This is where all the cool stuff happens, where we clean it up and change it. And finally, those new numbers go through a digital to analog converter, the DA box, to become the nice, clear sound you hear coming out of a speaker.
So that very first step, that analog to digital conversion, is what creates a discrete time signal. Instead of dealing with the whole messy, continuous wave, the converter just takes these tiny little snapshots, or samples, at super regular, super fast intervals. And the result? A sequence of numbers. Each number is just the height of the wave at that one specific moment. And just like that, the wave is officially digitized.
And this new digital form is amazingly flexible. This list of numbers can be shown as a graph. You can describe it with a math function, organize it into a table, or just keep it as a raw sequence of data. It's now pure information, and it's ready for us to work with.
Okay, so now our signal is just a bunch of numbers. This is where the real fun begins. This is where the power of DSP really shines. It's time to open up the digital toolkit.
I mean, think about it. We've turned a physical wave into a nice, clean list of numbers. And what can we do with numbers? We can do math on them. We can literally write a little program that says, hey, see that annoying background hum? Find those numbers and subtract them. Or find the numbers that make a voice sound thin and boost them. It's really that simple, but it is so powerful.
Let's look at two of the most basic tools in the kit. On the left, you've got time shifting. That's just sliding the whole sequence of numbers forward or backward to create something like a delay or an echo. And on the right, there's amplitude scaling. That's where we just multiply every single number in our sequence to make the signal stronger or weaker.
And this slide is a perfect example. That little formula, y of n equals 2x of n, it tells you exactly what's happening. It's just saying that every point on the output signal is double the value of the input signal. We're just multiplying by 2. This simple bit of math makes the signal stronger. For audio, that's literally turning up the volume. For an image, it's making it brighter. That is amplification right there in action.
Okay, so we have the signal as data, and we have the tools to change that data, but what is it that actually does the work? Well, that would be the system.
A system is just the thing that does the operations. It takes our list of numbers as an input, it applies the rules from our toolkit, and then it spits out a brand new, transformed list of numbers as the output. And this system isn't some imaginary box. It's a real thing, usually a special microchip, the digital signal processor. Or it's just a smart piece of code running on your phone's processor.
Now, not all systems are the same. A static system, for example, has no memory. Its output right now depends only on the input from right now. But a dynamic system does have memory. Its output can depend on what came before. And then you have causal versus non-causal. A causal system processes data as it comes in, only using past and present info.
That's absolutely essential for real-time things, like a phone call. But a non-causal system can look at the entire signal all at once. This is perfect for something like image processing, where the system can look ahead at all the pixels before it decides what to do with the current one.
So our signal has been captured, turned into numbers, and transformed by a digital system. What happens now? It comes back into our world.
That new, modified sequence of numbers gets fed into a digital-to-analog converter. It rebuilds the original wave from these new data points, and what you get is a new analog signal. But this time, it's been enhanced. It might be a voice on a call with all the background noise stripped out, or a photo where the colors are perfectly balanced. It's better.
And this brings us right back to that riddle from the beginning. Your voice? It's cleaned up by DSP so your voice assistant can understand you. A photo? It's sharpened and brightened using DSP and editing software. And those tiny tremors from an earthquake, DSP is used to analyze them and figure out exactly where the quake came from. And get this, those noise-canceling headphones, they're using a system that listens to the noise around you, and in real time, it creates the exact opposite sound wave and plays it in your ear to cancel the noise out. That is pure DSP at work.
So, here's the bottom line. Digital signal processing is the fundamental bridge that lets our digital devices see and hear and measure the analog world around us. It's a translator, a toolkit, and a workshop all rolled into one. Our entire digital world is built on these processed signals, which really only leaves one question. What are we going to build with it next?